Our understanding of the universe has been shaped by groundbreaking theories like general relativity and quantum mechanics. These two pillars of modern physics have provided us with profound insights into the nature of reality, each in its own unique way. General relativity beautifully explains the cosmos on a grand scale, encompassing the motion of planets, stars, and galaxies. It describes how massive objects like stars and planets warp the fabric of space-time, creating the gravitational forces that govern their movements. Quantum mechanics, on the other hand, delves into the microscopic world, unraveling the bizarre behavior of atoms and subatomic particles. It reveals a universe where particles can exist in multiple states at once, and where the act of observation can fundamentally alter the outcome of an experiment. These two pillars of modern physics have revolutionized our understanding of the cosmos, but they seem fundamentally incompatible. General relativity works exceptionally well on large scales, while quantum mechanics excels at describing the very small. Yet when we try to apply both theories to extreme conditions, such as those found inside black holes or during the Big Bang, they clash. This is where string theory enters the picture. It aims to bridge the gap between these two theories, offering a unified framework that can describe all fundamental forces and particles in the universe. String theory is a theoretical framework that attempts to reconcile these two seemingly contradictory theories into a single, elegant description of the universe. It proposes that the fundamental building blocks of reality are not point-like particles, but tiny, one-dimensional strings. It's a bold idea that has captivated the imaginations of physicists for decades. The potential of string theory to unify all known forces and particles into a single theoretical framework is both tantalizing and revolutionary. At its heart lies a simple yet profound shift in perspective. What if the fundamental constituents of the universe are not point-like particles as traditionally assumed, but rather tiny, vibrating strings? These strings can vibrate at different frequencies, and the different vibrational modes correspond to different particles. Imagine these strings as being incredibly small, far smaller than anything we can currently observe. They are on the order of the Planck length, which is about 10 ar 35 meters, a scale so minuscule that it defies our everyday understanding. Just as the strings on a violin can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different modes, giving rise to the diverse particles we observe in nature. Each mode of vibration corresponds to a different particle, such as an electron, a photon, or even a graviton, the hypothetical particle that mediates the force of gravity. The beauty of string theory lies in its potential to provide a unified description of all fundamental forces and particles. It suggests that the seemingly disparate phenomena we observe in the universe are all manifestations of the same underlying reality, governed by the vibrations of tiny strings. While string theory is still a work in progress and many questions remain unanswered, it represents a bold and exciting step towards a deeper understanding of the universe. It challenges us to rethink our most basic assumptions about the nature of reality and opens up new possibilities for exploring the cosmos. In the world of string theory, the seemingly infinite variety of particles that make up our universe are nothing more than different vibrations of these fundamental strings. Each vibrational pattern corresponds to a specific particle, with its unique properties like mass and charge.
Think of a guitar string. When plucked, it vibrates at a certain frequency, producing a specific note. Similarly, in string theory, each string's vibration determines its properties and characteristics. This elegant framework offers a compelling explanation for the diversity of particles and forces we observe in the universe. Electrons, quarks, photons, and all other particles, along with the forces they mediate, arise from the symphony of string vibrations. It's a beautiful and unifying concept. But string theory doesn't stop there. It proposes something even more radical: the existence of extraspatial dimensions beyond the three we experience in our everyday lives.
We experience the world in three spatial dimensions: up, down, left, right, and forward, backward. These dimensions form the very foundation of our physical reality, shaping how we interact with the world around us. From the simplest movements to the most complex structures, everything we perceive is bound by these three dimensions. These dimensions are intuitive and easy to grasp. Our brains are wired to understand and navigate this three-dimensional space effortlessly. We can visualize objects, predict their movements, and interact with them in a way that feels natural and instinctive. This understanding is so ingrained in us that we rarely stop to consider the possibility of anything beyond it. But string theory suggests that our universe might be far richer, harboring additional spatial dimensions that remain hidden from our perception. These extra dimensions are not just theoretical constructs, they are essential components of the universe's underlying structure. They offer a new perspective on the fundamental nature of reality, challenging our conventional understanding and opening up a realm of possibilities that extend far beyond our everyday experiences. These extra dimensions are not some fantastical realm, but rather an integral part of the fabric of space itself. They weave through the very essence of the cosmos, influencing the behavior of particles and the forces that govern them. By exploring these hidden dimensions, scientists hope to unlock new insights into the workings of the universe, potentially leading to groundbreaking discoveries that could revolutionize our understanding of physics. Imagine a tightrope walker moving along a cable. To the walker, the path seems straightforward, confined to a single line. This analogy helps us grasp the concept of limited perception within a seemingly simple framework. From our perspective, the tightrope walker can only move in one dimension, along the length of the cable. This linear movement represents our limited view of the universe, constrained by the dimensions we can perceive. However, an ant crawling on the cable experiences an additional dimension, the circumference of the cable, which is curled up and hidden from our view. This tiny creature navigates a world that includes an extra dimension, unseen by the tightrope walker, but very real to the ant. Similarly, string theory proposes that our universe may have extra dimensions that are curled up and compactified to such small scales that they are invisible to our current experimental capabilities. These dimensions could be wrapped so tightly that they escape detection, yet they play a crucial role in the fundamental structure of the universe. These extra dimensions, while hidden from view, play a crucial role in determining the properties of strings and the particles they give rise to. They influence the behavior of fundamental forces and particles, shaping the very fabric of reality. By delving into the mysteries of these hidden dimensions, scientists aim to uncover the secrets of the universe, potentially leading to a deeper understanding of the cosmos and our place within it. Section 4. The landscape of string theory. As physicists delved deeper into the intricacies of string theory, they discovered that it wasn't a single unique theory, but rather a collection of related theories, often referred to as the string theory landscape. Each of these theories describes a universe with its own set of extra dimensions and specific properties. These theories are like different solutions to the same underlying equations, much like a single mathematical equation can have multiple solutions. This realization led to the concept of the multiverse, the idea that our universe might be just one of many universes, each governed by its own set of physical laws and constants. While the idea of a multiverse is highly speculative, it has profound implications for our understanding of the universe and our place within it. Section 5. String theory and the mystery of gravity. One of the most remarkable achievements of string theory is its ability to naturally incorporate gravity, a force that has long resisted unification with the other fundamental forces of nature. For decades, physicists have struggled to reconcile gravity with the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. String theory offers a promising solution to this long-standing problem. In Einstein's general relativity, gravity is described as the curvature of space-time caused by the presence of mass and energy. This revolutionary idea transformed our understanding of gravity from a force acting at a distance, as Newton described, to a geometric property of space-time itself. Objects move along the curves and contours of space-time, much like marbles rolling on a curved surface. This analogy helps us visualize how massive objects like planets and stars influence the fabric of space-time, creating the gravitational effects we observe.
String theory provides an elegant explanation for how gravity emerges from the vibrations of strings. These tiny, one-dimensional objects vibrate at different frequencies, giving rise to the various particles and forces in the universe. Closed loops of strings, known as gravitons, are thought to be the fundamental particles that mediate the gravitational force. Unlike other particles, gravitons are unique in that they are massless and travel at the speed of light, allowing them to interact with the fabric of space-time itself. When these gravitons interact with other strings, they cause space-time to curve, giving rise to the force of gravity that we experience. This interaction is a key aspect of how string theory unifies gravity with the other fundamental forces, providing a more complete picture of the universe's underlying structure.
This natural incorporation of gravity is a significant achievement for string theory, as it provides a framework for understanding how gravity might be unified with the other fundamental forces at the most fundamental level. By offering a coherent and mathematically consistent description of gravity, string theory opens up new possibilities for exploring the deepest mysteries of the cosmos, from the behavior of black holes to the origins of the universe.